So today we look at rates of change in the natural and social sciences, which is section 3.7 in our book. And we're just going to see that these rates of change, or what we call derivatives, occur in all the sciences. So as an example, in physics, we have velocity, which is change in position with respect to time. We have density, which I think we've looked at one time or another, and you'll see again. We have current, which is measured in amps, and it's a change in charge with respect to time. There's power, which is change in work or energy with respect to time. And we'll see some of these in our calculus class. Chemistry, we have rate of reaction. And compressibility. And there are others also. These are just some of the things that you may see if you study in these various fields. Biology, of course, you have these growth rates, or rate of growth. We'll see growth rates in this class. I've got another example is the blood velocity gradient. And this, if you're interested, this is talked about in our book on page 230. In economics, we have, we've got marginal cost. And there's also marginal profit and marginal revenue. We'll see some of these in this class. Basically in econ, when you see the word marginal, it means derivative. So that marginal cost is a rate of change or a derivative of the cost function. In geology, we have the rate of heat flow. In psychology, there is the learning curve, which is really a rate of improvement in performance. So, learning curve. Sociology, we have one thing. These things that I'm mentioning are just some of the rates of change that occur in these fields. So sociology, there's a rate of change called the rate of spread of a rumor. Or a fad. And of course, these have changed in recent times because of the ability of things to spread very quickly online. Our book has an example of this on page 206. It's kind of interesting. There's a mathematical model of that. It's problem number 84. In case you're just out of curiosity, page 206, number 84. You can measure things like phrases that come into play. Like, I remember the first time I heard the phrase "my bad." It was, I think, in the 90s, and somebody said "my bad," and it was like, what are you talking about? Now, of course, it's just common everywhere. And things like phrases like "I know, right?" Okay, and in 1975, nobody said "I know, right?" It just makes an appearance and then keeps going. There's older ones, like you guys have probably never said, or very rarely say, "That was a hoot." But at one time, that phrase was the new phrase. I don't know when, a long time ago, though. And there's things like, here's a new one. This is almost embarrassing to say because it's so strange, but "on fleek." And I think my students tried to teach me that one. I had no idea. It has to do with eyebrows, apparently. Can't be used for math lectures, I found out. But there's these phrases that appear in cultures. They can be modeled sometimes to see how fast they spread. So anyway, these are all just special cases of a single mathematical concept, the derivative. derivative is a rate of change. The geometric equivalent is a slope of a line, like we saw when we were first defining the derivative. We defined it as an instantaneous rate of change, which geometrically appears when you're comparing two variables, like on the xy plane, as a slope of a line. And it's an illustration of the fact that part of the power of mathematics lies in its abstractness. So a single abstract mathematical concept, such as the derivative, can have different interpretations in each of the sciences. And there's this mathematician, Joseph Fourier, which some of you, anybody who's going into electrical engineering will definitely study Fourier's series. And some of you, even if you're not in that field, will see it because it comes up from time to time. And many of you will study the Fourier series. And there's a quote attributed to him where he said, "Mathematics compares the most diverse phenomena and discovers the secret analogies that unite them." So we'll take a look at an example from economics. And one thing about econ, the mathematical models that economists use are often low-degree polynomials, and they can use these to illustrate complicated phenomena like cost and revenue. But you'll notice if you compare the models from econ to the ones in physics, the ones in physics are usually much messier and they're much more accurate and very precise. So if I were to drop a pencil from 5 feet, we could with mathematical models, we could describe a lot about that pencil. How long it would take it to hit the ground, how fast it would be traveling when it hit the ground, and different physicists could do the calculations and they'd all get the same answer. Whereas in econ, you can't really have controlled experiments where you can control your variables very precisely, and there's just so many variables, so you don't have the precision of the models. So you want a model that can be used to make good decisions, but you don't expect it to be precise like a physics model. And so you'll just notice when you see econ models, they're usually much easier to work with. They're polynomials. There's like disagreement often. So like in physics, physicists typically don't disagree on what's going to happen when I release a pencil. But in econ, there's often disagreement along like party lines as to what will happen in the economy. And it's more difficult. You can't control variables. You can't go into a state, let's say, and control all the money and start experimenting with what happens as you release money into the economy. So you just notice that, and you'll see it here. Our mathematical models for econ are typically just polynomials like the one we've got here. So for this one, it says, suppose the cost of producing X hoverboards is, and they have a mathematical model for the cost function. One thing we should always do also, when you look at our model, make sure we understand what these variables are. So it says the dollar cost of producing X hoverboards. So X is the number of hoverboards. And when I plug in the number of hoverboards here, this model will give me the cost. It's a cost function. So it says, find the average cost per hoverboard of producing the first 100 hoverboards. Well, first, let's figure out what's the cost to produce these 100 hoverboards. So we can use our model up here. Remember, X is the number of hoverboards, so X is 100. So I'm going to plug in 100 here and here, and that will give us the cost of producing those first 100 hoverboards. So we have cost of 100, which would be equal to 2,000 plus, see, 100 times 100 minus 0.1 times 100 squared. So if we go through the arithmetic here and do the math, we'll get $11,000. So we found that we didn't find the average cost. We found the cost of making 100 hoverboards. Now they want the average cost per hoverboard. So we just to find the average cost, we take this and divide it by 100 so that the average cost equals 11,000 divided by 100. Total cost divided by how many there are. And then we would come up with $110 per hoverboard. Then they want us to find the marginal cost when the first 100 hoverboards are produced. So marginal cost, remember what this is. Marginal cost is the rate of change of the cost function. So earlier we saw a graph of a cost function, and we saw it's not linear, it changes. I suppose we could have an example where there's a linear cost function, but the marginal cost is going to change depending on where we are. So you have economies of scale, which we had mentioned. A lot of times when you're making just a handful of items, it's more expensive, and as you make more and more of them, it becomes cheaper. So the marginal cost is going to depend on where we are. So they're asking us for the marginal cost, which is basically the derivative of the cost function, at this point when we've made 100 hoverboards. So remember, marginal just means derivative. The derivative of the cost function, marginal cost, when this many hoverboards are produced. Well, we have our cost function here, so we can definitely find the marginal cost. So the cost function is c of x. Marginal cost would be c prime of x, and it's a pretty easy derivative to take. We just use a power rule. So we've got c prime of x, the marginal cost, rate of change of the cost function, and we take the derivative, and we will get, see, 100 minus 0.2x. So we've got our marginal cost function, and then to find it when 100 hoverboards are produced, we just have to plug in 100 here. So let's do this. So c prime of 100, so the marginal cost at that point when 100 hoverboards have been produced will be 100 minus 0.2 times 100, which gives us $80 per hoverboard. And there's a note here. It says, note, this is the approximate cost of producing one more hoverboard at that point. So this is the rate of change of the cost function at this point, which means that the cost function is changing by $80 per board, per hoverboard at this point, which means basically if we're here, we've made 100 hoverboards, the next hoverboard we make is going to cost $80 to make. And you may even notice that over here, the average cost of the first 100 hoverboards is $110 a board. But at this point, think of the assembly line is cranking out these hoverboards, and at this point, it's cheaper, right? We've made a bunch of them. So at this point, because of economies of scale, then the board is only $80 a board, even though on average for the first 100 it's $110 a board. And now we're asked to show that the marginal cost when 100 hoverboards are produced, which is what we just found, is approximately the cost of producing one more hoverboard after the first 100 have been made by calculating the latter cost directly. So to calculate that directly, make a little more room here. To calculate it directly, we could just say, well, let's figure out the cost of producing 101 hoverboards and subtract the cost of producing the first 100 hoverboards, and this would leave us with the cost of producing that 101st hoverboard, which basically is what we calculated here using the cost function, or the marginal cost function. Right? We said that at this point, hoverboards, the cost function is changed by $80 a board, which means that the next board that comes out of here, the 101st board, would be about $80 to make. And then this will use the cost function instead of the marginal cost function to calculate this directly. Say, how much does it cost to make 101 boards? Subtract off the cost to make 100 boards, the first 100 boards, and that would leave us with the cost to make the 101st board. And we can calculate this just by using the formula above. So the cost function at 101 boards would be 2,000 plus 100 times 101 minus 0.1 times 101 squared minus this cost, which we already calculated, right? We calculated this cost, and that cost was $1,100. So I'm going to subtract off $11,000. So I'm going to subtract off the $11,000 here. So then when we calculate this, that ends up being $11,079.90. We subtract off the 11,000, and we will end up with $79.90, which is pretty close to what we got. So if you remember, we are using a continuous curve to approximate a discrete concept. Because if you remember, really, like, if we have this cost function, really what's happening is we're going to have a break here in the number line. But just think, at this point, we've got 100 hoverboards, 101. So it's not, the cost function truly is not a continuous function, because these values in between here don't make any sense here. You're going to have 100 or 101 boards, but the cost function at 100.2 doesn't really make sense. So when we talked about earlier, this cost function is really a discrete function, but we're approximating it with a continuous curve. So that's why these are going to be a little bit different. But oftentimes it's easier to do this calculation. So economists will do this calculation, and it's close to this. And remember, we don't expect these to be precise. These are not physics formulas. So if you could come up with a model that accurately predicts the stock market or financial markets, you could be extremely wealthy. But they are too complicated. So these econ models are not expected to be great precise models. They just have to be good enough to be used to make good decisions. And now we'll look at some physics applications. And the textbook that we use, the Stewart calculus book, and also the another one that's very common is the Thomas calculus book. Those two have a lot of the market share in the United States in calculus classes. Both of them have a lot of physics applications, and I guess calculus lends itself to physics nicely, and a lot of the students who take these books are going into applied fields where they'll see physics. So I guess it makes sense. And so let's take a look at this application from physics. We're talking about rates of change. And something that we've mentioned before is if you have a position function and you're interested in finding how fast position is changing with respect to time, you have velocity, which is basically, here's the position function, f of t. Velocity is the derivative of the position function, f prime of t. And then acceleration is the second derivative of the position function, or the derivative of the velocity function. So just to get a little used to the units of measure we'll see often, position will often be given in meters or feet. If it's given in meters, remember we have one-dimensional motion only in Calc 1 and Calc 2. We have one-dimensional motion. Calc 2, there's some exceptions where you'll have parametric equations or polar equations where you can move around. But for the most part, we're talking about motion just up and down motion, or left and right motion, because we don't study vectors yet. So position, up and down or left and right, we've got, if it's in meters, and then if you're going to talk about the velocity, which is change in position with respect to time, often time will be in seconds. So velocity would be measured in meters per second. And then acceleration, which is the derivative of velocity, so it's the change in velocity with respect to time, right? Time is our independent variable in all these cases. So acceleration, the units would be the meters per second, which is typically written as meters per second squared. And again, it's just because it's a little awkward to write meters per second. So we do the mathematical equivalent of, instead of dividing by seconds, we could multiply by the reciprocal of seconds, right? So let me clean this up a little bit. So if we have meters per second. Instead of dividing by seconds over 1, we multiply by the reciprocal, which would be 1 over seconds. And then you can see, because when you multiply fractions, you go straight across, you can do meters divided by second squared. So that's where this notation comes from. So the problem that we're looking at, they give us the position of a particle, and they give us this position function. It says t is measured in seconds, so t, our variable here, is in seconds. So we plug in seconds, and then s is in meters, so it'd give us the position in meters. So one thing that we had to remember, though, is that this function is not the path of the particle. It's not the path of the particle. The particle is traveling in a straight line, probably in this case like a left-right. So we could think of it as when it's moving to the right, we'll think of it as having a positive velocity. And when it's moving to the left, we'll think of it as having a negative velocity. Those are arbitrary, but that's typically how it's done. Also remember that when we talk about this particle, the particle could really be the center of mass of a boat, a plane, a planet, a car, an asteroid, a piston, a flywheel. I mean, it could be just about anything, so it's not really meant to be just a, we're constantly talking about these particles. We'll find out in your physics classes that if you treat the center of mass like a particle, you can use the same models. So let's see, a couple of notes here. These are things that we had mentioned before, but just to make sure we're good on this. Note 1, the particle is moving in a straight line. We always use straight line motion, Calc 1 and Calc 2. Calc 3, you learn about vectors. You'll probably learn about those in physics also, and then you'll be able to have motion that's not in a straight line. And the second one that I mentioned is this function f of t. This position function is not the path of the particle. Because that function is a cubic, and it most definitely could not be straight line motion with that, right? So that is going to tell us what position we're in along a number line at any time t. So they want us to find the velocity at time t. Well, we've got the position function, so the velocity is just straightforward. We just take the derivative of the position function. That'll give us our velocity function. So the velocity at time t would be v of t, and we just use the power rule here, so we'll get 3t squared minus 24t plus 36. And now this will give us the velocity of this particle at any time t. And the velocity will be in meters per second because t is measured in seconds, s is measured in meters. And remember, whenever you have these mathematical models, always make sure you're clear on what these represent. T is time in seconds, and then s, or the function itself, f of t, gives us the position of the particle. Think of it as just being along a number line. It's going to give us a number, and that number is the position on the number line here. So we've got our velocity function. Then it says, what is the velocity after 1 second or 3 seconds? So we've got a formula for any number of seconds. So we just use this formula, plug in 1 for t, and then plug in 3 for t. So let's go ahead and move this up a little and see what we get here. So the velocity after 1 second is going to be 3 times 1 squared minus 24 times 1 plus 36. And that would give us 15 meters per second. And if we repeat that same thing at 3 seconds, we get 3 times 3 squared minus 24 times 3 plus 36. And if you go through the math there, you'll get negative 9 meters per second. And then let's make sure we're clear on this negative velocity. Well, remember, we don't have negative speed. Speed, if you remember, if you take the absolute value of velocity, you get speed. So speed is always going to be positive. Just like you'd expect when you drive backward in your car, the speedometer doesn't give you a negative number. Speed is the magnitude of velocity, and so it'll always be positive. But velocity here, this is telling us a direction. We have straight line motion, so when it's negative, typically that means we're going to the left or down. And so in this case, we know that on a number line, if you think about if this is left-right motion on a number line, so we're going along here. And in this first case, 15 meters per second. So if we have some number that is the origin, or 0 on the number line, 15 meters per second means we're going in this direction. We're going to the right at 15 meters per second. But -9 on left-right motion means we're going to the left. We're going in this direction, 9 meters per second. And if this were, say, a dropped ball problem, which we'll see at some point, so then we have up-down motion. In that case, a negative velocity would mean we're moving down. Positive velocity, we're moving up. So if you keep that in mind, these will be much easier. These position functions don't give us the path of the particle, they give us the location on a number line. Another common question with a position function is, when is the particle at rest? Well, it will be at rest when the velocity is 0, right? When the rate of change is 0. So when they ask us when is the particle at rest, we just have to take our velocity function up here and set that equal to 0 and see at what time that happens. Remember, our independent variable is t for time. So let's take a look, see what we get. So we have the velocity is equal to 3t squared minus 24t plus 36. We want to set this equal to 0 and solve for t. So we are solving this equation for t. So we've got a second degree equation. So if you remember second degree equations to solve, sometimes you get a little rusty on this, but a second degree equation, there's a couple things you can try. We could try to factor. By factoring, if we turn it into a binomial times a binomial equals 0, then we can use the zero product property, which basically says if this thing times this thing is 0, then it could be that this is 0 or this is 0, right? So with a second degree equation, sometimes you can factor. We can in this case, this one does factor, but sometimes you can't factor. It might be an irreducible quadratic, so we can't factor it. But we do have a go-to method that works 100% of the time, and that is the quadratic formula. But one way or another, we need to be able to factor, or we need to be able to solve second degree equations. We're going to be solving them all the time. So if you're rusty in solving second degree equation, you really should practice that. Practice either factoring or the quadratic formula. Quadratic formula always works. But just to get a little practice with factoring, because sometimes we're rusty on that. Let's say I'm going to factor this. Well, I'm going to factor it so that I can solve it. So first, since I'm solving this and it's equal to 0, you can see they got a common factor of 3. And since we're solving it, we don't need to keep this extra factor. Like if this were a different problem and the equal 0 wasn't here and all we had was this right here in algebra class, and your teacher said, hey, factor this. Well, when we factor, we have to factor out that 3, and that 3 stays with it, right? So if we were truly just going to factor, I would factor this 3 and we get t squared minus 8t plus 12, and we would then factor this inside and we'd keep the 3. But for us, we're factoring as a means to an end. We want to solve this. So when I'm here, I really don't care to factor this where I keep the 3. We're solving it. So I can divide both sides by 3 right here. I can divide this side by 3, left side, and the right side by 3. 0 divided by 3 is still 0. So if I divide this by 3, I'm just going to get rid of the 3. So since we're solving this, we have an equation set equal to 0, and I can do anything I want on the left as long as I do the same thing on the right. I can just divide everything by 3 and just get rid of this 3. we don't really need the 3 there. So what we've got is just this. So we don't really need these either. All right, so now what we want to do is just factor that so that we can solve. And with a guess and check method, some of you may have learned the AC method, but just because we don't cover that in here, I'm just going to review with the guess and check. Guess and check method is sort of like we're trying to do the FOIL method in reverse. So if you remember, the FOIL method is when we multiply 2 binomials together, and just an acronym to remember how to distribute properly. So we have first times first, outside times outside, inside times inside, last times last. And when we would do that, we would get back here. So with guess and check, we do this backward. We think, okay, first times first has to be t squared. So what does this and this have to be? And this one's kind of easy. It's going to have to be t times t. Then we think, okay, last times last. Last times last has to be 12. So it could be like maybe 1 and 12, 2 and 6, 3 and 4. But the deciding factor is that the outside and inside terms have to add up to -8. So just think, okay, 1 and 12, I'm not gonna be able to make that work. 3 and 4, not really, but what about 2 and 6? If I put a 2 here and a 6 here, and then I think, okay, so last times last is 12, and outside times outside is 6t, inside times inside is 2t, I could make that add up to -8t if I made them both negative. And then you can verify if you FOIL this, you'll get back here. Because outside times outside does add up to -8t. And now, so we've got this binomial times this binomial is 0. So to make that happen, either of these could be 0. So it could be that t minus 2 is 0, or it could be that t minus 6 is 0. If I add 2 to each side, I get t equals 2. Add 6 to each side, I get t equals 6. So basically, the particle is at rest at these 2 times. These values, if I plug into the velocity function, will give me a 0. And you can try it. If I plug in a 2 here, I get 3 times 2 squared, which is 3 times 4, which is 12. Minus 24 times 2, which is minus 48. So 12 minus 48 is -36, plus 36 is 0. And the same thing would work for the 6. So let me just add this. Okay, so the particle is at rest at t equals 2 seconds and t equals 6 seconds. So the next question is, when is a particle moving forward? Moving forward, or in the positive direction. So in this case, you could also, maybe they could say, when is a particle moving to the right? You could think of that as being the same question. Or if this were up-down motion, they'd say, when is a particle moving up? But they make it really clear when they say positive direction, so we want velocity to be positive. So a little note here is the particle moves forward or to the right when the velocity function is positive. It moves forward when the velocity is positive. It moves backward when velocity is negative. So to do this, we can take our velocity function, just like before, 3t squared minus 24t plus 36. And this time we don't set it equal to 0, we set it greater than 0. And now you've got an equation that you would have seen in an algebra class where you're solving an inequality. And it's a second degree inequality. So typically the way this is taught is try to find out where this is 0 first. Where's this 0 first? Because you can break up a number line at those points. And we did that already. So just repeat the process. What we did is we divided each side by 3 to get here. And then we factored t minus 2, t minus 6 is greater than 0. And so what we want to do now, we found the zeros here are 2 and 6. So when you're solving inequalities, you first break up the number line at the zeros. So I'm going to take this number line and break it up at 2 and 6. And then we just need to figure out when is the velocity positive. And the way you can do that is just pick a number here and plug it in for the velocity. And it's easier to plug it in here while it's broken down. You could plug it in here too, but it's much easier here. So you pick these test points. So maybe you pick like, well, let's see 1, 3, and 7. Basically, here's a number line. This is in seconds. And since we know the velocity function is 0 only here and only here, right? It's not 0 at any time between 2 and 6. It's only 0 at 2 and 6. So if the velocity is positive at 3 seconds, it will be positive at 4.9 seconds or at 5.2 seconds. It can only switch at these 2 points. So because of that, we can just pick a number in these regions and see what the velocity is there, and it will be there throughout the region. So whatever the velocity is doing at 7 seconds, it's doing that at 1,000,000 seconds because there's only 2 points where this is 0. So to pick these test points, like 1, I'm just picking easy ones. I could have picked 1.7, right, and plugged it in here or here, but it's much easier with 1. And the easiest way is to use this, because all I need to know is if this positive here or negative here. So if I plug this 1 in here into the velocity formula, again, I could plug it in here, but it'll be the same answer here and much easier. If I plug a 1 in here, I get 1 minus 2. So just think 1 minus 2, so I'm using this point here, 1 minus 2 is going to be a negative number. Then I plug a 1 in here, 1 minus 6 is another negative number. And then I multiply these, so negative times negative is positive. So I know up here, the velocity is positive here. And then I know the velocity is 0 here, so let's see what it does on this region. So if I plug the 3 in here, 3 minus 2 is 1, that's positive. So basically what I'm saying is we don't have to calculate the number to know what it is. We just need to know if the number is positive or negative. And I know when I plug a 3 in here, I'm going to get a positive number. Put a 3 in here, 3 minus 6, that's going to be a negative number. And then when I multiply those two numbers together, I get positive times negative, so I'm going to get a negative. Which means that velocity on this region is negative, which means on this region, from 0 to 2, because we start at time 0, from 0 to 2 seconds, the particle is moving forward. Then at 2 seconds, it stops, and it starts to move backward, and it goes backward till 6 seconds when it stops. And then let's see at that point, does it continue backward or does it switch and go forward? We'll do that by plugging this test point of 7 in here. So if I use 7, I'm going to get a couple of numbers here, positive or negative. Plug a 7 in here, 7 minus 2 is positive. Also 7 minus 6 is positive, so I have over here positive times positive, which again is positive. So that means that the particle here, it hits 0 and then it starts moving in a positive direction. So looking at this, we could say the particle moves forward when t is less than 2 and when t is greater than 6, right? And the particle moves backward between 2 and 6 seconds, which we could say something like this. I didn't put less than or equal to because we know at 2 and 6 seconds it's not moving, right? The velocity is 0 there. So that's how we figure out forward or backward also direction. And then one other thing they'll have us do is draw a diagram to represent the motion of the particle. So the thing to keep in mind here is we have to do this in a way where we can see what's happening, because think if I just drew a line. So think if I'm starting right here, I'm going to start at this point on the line and I say, okay, the first 2 seconds it moved forward, and then it moved backward, and then it moved forward. I can't really see what's happening. So what we're going to do is take this number line and sort of lift it. So we'll do things like this. We'll say it's moving forward here, then it turned around and moved backward, then it moved forward. So it's not really turning like this. It's just a way of us being able to demonstrate the movement without going back, because we know it's straight line motion. So this is just a way that we can kind of tell that, oh, it stops here, then it went backward. So our diagram will look something like this. So let's take a look and see what we're going to get here. Let's get this out of here. And it says draw a diagram to represent the motion of the particle. So what we want to do is have some sort of number line here. And this will be our position. This is our position S at time t. So to see where we first start, we've got, we've got our position function, which I'm going to rewrite down here because it's up there a ways on the screen. But here's our position function. S equals f of t, which is equal to t cubed minus 12t squared plus 36t plus 18. So we could figure out where we are initially when time is 0. So where on this number line are we initially? Where is our position when time is 0? So if I plug in a 0 for t, so this function of time, if I plug a 0 here, here, and here, I'm going to get 18. So we're basically saying when we first start, we are at 18 on the number line, and here is where we start. And a lot of times we do something like say, okay, at this point, t equals 0. Here's our starting point. Here's our position. Here's a number line that shows us our position. We're at 18 on the number line. At time equals 0, we're starting here. And now we know that we're going to move forward. We're moving forward for the first 2 seconds. So let's see where we are at 2 seconds. Because remember, the numbers that we're kind of interested in are 2 and 6. So we stop moving at 2 seconds. So let's see where we are at 2 seconds. So what I have to do is plug in 2 here and find the position at 2 seconds. So if you take a 2 to find f of 2, we basically have 2 cubed minus 12 times 2 squared plus 36 times 2 plus 18. And if you go through the arithmetic here, you get 50. So I'm going to go to the number line here, and let's say there's 50 there. And so basically this particle, for the first 2 seconds, is moving along the right. And then here's where we're going to do that little curve. So I put a little curve here. So at this point here, so it goes to this point. At this point, t equals 2. And we know that at this point, the particle stops, and now it starts to go backward. And we know it's going to go backward until it hits 6 seconds. So let's figure out what f of 6 is so we can find our position at 6 seconds. That's going to be 6 cubed minus 12 times 6 squared plus 36 times 6 plus 18. And if you do that math, we get back to 18 again. Now this doesn't have to be the case. It doesn't have to be that we get back right here, right at 18 again. This problem we just happen to. So to draw a diagram to represent the motion of the particle turns around and goes back here. And again, I'm going to kind of curve it up so we can actually see the motion. So at this point, we're at 6 seconds. And we're back here where we started at 18. Our position on this number line is at 18 meters. And then from here, it's going to be moving forward from that point on, right? It doesn't go back. So then from here, we can just do something like this and just realize that it just keeps on going. It's not going to change, but it's not going to stop again because it only stops at these 2 times. So it's just going to keep on going. And then you also notice that a lot of times we'll put these little arrows on here just to make it easier to see the direction we're moving. So just if somebody's looking at this, they can say, okay, here's time equals 0, we're going over here. Time equals 2, we stopped, we turn around, we're going back here. Time equals 6, we stop again, turn back around, and we're going over in this direction. The last thing we need to do is find the total distance traveled by the particle in the first 10 seconds. So we have to think of what's happening here. So here's what we can't do. We can't say, well, let's see, it started here and moved in this direction, then it came back, and then it turned around, and find like where are we at 10 seconds and say, oh, here's the distance, right? So to find the distance, that would actually give us a displacement, which we don't cover in here. But the distance, we have to add up these little distances where it was going in the other direction. So when it turned around here, we need to take both of those distances, and then we have this other distance. We have to add all this stuff up. So we're going to have to break up, to find all these individual distances, we're going to have to find the distances between these individual points, like from here to here, what's that distance? Then from here to here, what's that distance? Then from here to wherever 10 seconds is, what's that distance? That's really what we have to do. So with that in mind, the little note is we need to calculate these little individual distances. So we need to calculate distances traveled during these time intervals. So let's think of it between 0 and 2 seconds, that distance. Also between 2 and 6 seconds, that distance. And also between 6 and 10 seconds. So we need to just individually find these distances and then add those 3 up, and we'll have the total distance traveled in the first 10 seconds. So let's do these one at a time. To find these distances, let's go from, say, 0 to 2. So for this one, we need to figure out the magnitude of f of 2 minus f of 0. I'm using absolute value because we want distance. We want to figure out what was our position at 2 seconds and subtract that from our position initially at 0 seconds. And then we're going to take the absolute value because we want distances. So if we don't want these canceling out. So if one of these gave us a negative number, we wouldn't want it to cancel, right? We don't want these to cancel out because they're going in different directions. So we use absolute value to get the magnitude of this change, and that'll be the distance. So f of 2, that's one of them that we figured out actually. We plugged in 2 into the position function and we got 50. So this number is just going to be 50 minus f of 0, which is 18. 50 minus 18, and we're going to get 32 meters. So the particle traveled 32 meters in the first 2 seconds. Okay, then we have to think about what about between 2 seconds and 6 seconds. Well, that's just going to be f of 6 minus f of 2. Right, find the position after 6 seconds, subtract the position after 2 seconds. We did those also earlier. We saw that it came back to the starting point. So subtract here, and this gives us another 32 meters. Again, it's positive because these absolute values. We want distance. If we want distance, we can't use negative numbers, so we take the absolute values. So basically, the particle went 32 meters to the right. It stopped at 2 seconds, then took the next 4 seconds going back 32 meters to right where it started from. Right, so it was going slower on the way back. It took 4 seconds to get back, only took 2 seconds to get there. Now we know at 6 seconds it stops moving again. So let's figure out what happens, the distance between 6 seconds and 10 seconds. So that's going to be position function at 10 seconds minus the position function at 6 seconds. And the position function at 10 seconds, if you plug 10 into our original position function, you get 178. So this is going to be 178 minus 18, which is our position at 6 seconds. And that gives us 160 meters. And just to make sure, f of 10, this is our position function at 10 seconds. So go back to our original position function, which was that t cubed minus 12t squared plus 36t plus 18. Plug in 10 to that function to get 178. So then we want to find the total distance traveled in the first 10 seconds. We just have to add these up. So if you add these up, you get the total distance of 224 meters. That is the total distance traveled in the first 10 seconds. Now that should put you in good shape to work on the problems from that section, from section 3.7. So give them a try, and if you have any questions, just let me know.